Live. Welcome back to Zero X Hack. My name is Antoni Chaniewicki, and with me is Jordi Baylina from Hermez Network. Welcome, Jordi.
Thank you very much.
I'm very happy to have you. I really enjoy Hermez Network. And today you're going to tell us about token transfers and scaling them on Ethereum. So the stage is yours.
Thank you very much. Let's go. Okay, my presentation will have like two parts. The first, I will do a quick introduction, a very practical introduction to zero knowledge, what zero knowledge, how it works, and how can you use the zero knowledge. And the second part will explain how we apply this technology and this tooling to the Hermes network rollup. So, well, let's start. Let me just here. Okay, what's a zero knowledge? If you go to Wikipedia, probably it's the worst way to learn what's zero knowledge. So let me explain you the more practical way what's a zero knowledge. The best way to understand it is imagine that a deterministic circuit, a deterministic program, if you want. So it's just you have a program that you have an input, and given an input, you get an output, and you always get the same output given for a given input. Okay, a deterministic program. This can be a computation, and that can be, for example, a heavy computation or whatever computation it is. Okay, so if I give you the results and you want to know that these results of this program is okay, well, the easiest way to test it is just run the program again. You just put the inputs, you run the program, you see that gives the outputs, and then you are sure that this result is valid. Okay, but you need to run the full full program to see it. There is a technique, there is the zero knowledge. What you can do mainly is there are two things you can do is you can prove that this computation is valid without having to compute the full program. If the program may take, for example, one, you need to run the full program again. Okay. The other thing of zero knowledge, and here is where the word comes, the zero knowledge, is that you don't even know what input. You don't need to know what input is valid. You just get the output. You know that the output is a result is valid, but you can hide the input, but you know for sure that the computation was created. To see this, well, this intuitively is very difficult to see it unless you have a deterministic circuit that's unreversible. For example, a hash circuit. Okay, so imagine that you have a deterministic circuit that you get an input, you hash it, and you get the output. Okay, so when you have the output, if I give you an output, if I give you a result of a hash, how can you be convinced that this output, this number, is compute from a hash, or it's just a random number that I just get it out of my pocket? Okay, so the thing is, of course, if I give you the input, then you can compute the hash, and then you see that's the output. That's easy. But imagine that I don't want to give you that input. It's a hidden value. I promise you that this input is I have an input, I compute a hash, and this is the result of a given hash. So I want to prove you that I know this input, that when you hash it, you give this number, but without having to give you this number. Okay, well, this you can do it. This is also zero knowledge. So you actually you give the output, you give the proof of this circuit without revealing the input, and the verifier can be convinced cryptographically that this output was generated given a given hash, so that you know, and proving so that you know this input that gives this hash. Okay. So when you apply a unreversible, so a deterministic program, a circuit that's that these applications have a lot of sense. Another example, if you want, for example, is factoring two prime numbers. I give you an output, maybe the multiplication of two prime numbers, and I want to prove you that I know the two prime numbers, that actually when you multiply them together, it gives an output. Okay, so I want to explain you. I want to. This is the main explanation of what zero knowledge. Okay. So what I want to do now is just I want to show you how to work. So how to do it that in real life. So let's create a circuit. Let's create a deterministic program. Let's create a proof, and let's verify that. Okay. So let's do all the full process all together. Okay. So in order to do that, let's work with a simple program. Okay. So it's a program is just a program that actually computes so that I give you a number and I want to prove you that I know two numbers that when you multiply them together, it gives that number. As you know, factorization is not easy. So if you have the two numbers, you can prove easily that when you multiply them together, it gives the output. But if you don't know these two inputs, then it's much more difficult. Okay, so here is how would you write it in Circom. Circom is a zero knowledge. It's a language for writing these deterministic programs that can be used in computing in proof systems. You know, in Zika snarks or more recently in Plonk. Okay, so that's how do you it's a circuit, it's a language to write these deterministic programs. So here is a first deterministic program. It's a very simple, it's just like a hello world of this program. Okay, so here we define we define a multiplier. Okay, and we define two inputs that are private, of course, because I don't want to reveal them. I have an output, and then I just assign that the output is just A times B. Okay, and then I just instantiate this template. Okay, so this would be an example of a program. The problem of this is that in general, the circuits when you're generating these programs, you cannot. It's like you cannot do like everything. Okay, the first thing is that all the signals, you know, all the variables that are inside, must be from the field number. Okay, and also, okay, for example, this is a very easy because, for example, I can the other problem of this circuit. So if it's a field number, then factoring a number in field number, that's quite easy because just finding the inverse of any number, and any number can be multiplied by another number and give this number. So it's not a good thing. And the other thing that's important is that you can always use one. You know, if one of those is one, the other is just the output, and then this is always gives the two. So this circuit would not be very practical. Okay, to do it more practical, well, we need to write different things. Okay, so this is not the last one. But in any case, the first thing is one thing that we have to do is, for example, is just see that there is no overflow. For example, we limit the input A and the input B that has only 64 bits. So this is how you would write it in Circom. Mainly what we are doing is we are decomposing each number in a binary field, and then we check that each of these binary element is just 0 and 1. Okay, so this is this constraint. Let's see, oh, no, this is not. So you see here. I don't know. It's a pointer somewhere. Okay. Well, here you see in the bits. The bits is 8. So bits I times bits I minus 1 equals 0. That means that bits I must be binary. Then we do that for all the 64 bits, and then we can join them together. Circom has the advantages that you build like hardware. Okay, so you build a component that does something, and then a component can be made of subcomponents, and each subcomponent can be made in subcomponents, and then you just divide and conquer technique, and then you just join the blocks together, and you can build whatever you want. Okay, so let's create. If you want, let's start with this simple circuit. Okay, so this template. So what I'm gonna do is now I'm gonna switch. Okay, and let's create that. So let's compile that circuit and let's create a proof on that. So let's do it fast. Okay, so in order to do that, let me just create. Let's see. Let me do it big. Okay. So I hope that you can see the screen more or less. Let me just do it even bigger. Okay. Let's create the 0x example. 0x example. Okay, and I create this. Okay, so let's cut and paste this circuit. Just the way it is. Okay. Okay. I have a simple file that says circle. Okay, so now what I'm going to do is, well, I can do npm install circom -g, install it globally. Okay. Save it, finish. Okay, and then I just do run circom, the circuit, and here I want to generate a R1CS constraint. I want to generate the WASM code to generate the witness. The witness is all the intermediary signals of this circuit that so I generate here a WASM file, and I want to generate also the symbols, and I do it in well, I just do this. Okay, so I run this. Okay, and if I see here, so I have the circuit.com, here I generated 3 files. Okay, the R1CS file is like the result of the compilation. This is mainly all the constraint systems where all the intermediary signals, you see all the constraints. Okay, you have the symbol, it's like a symbol table mainly for debugging and all that. And then we have a WASM. That's an actual WASM WebAssembly source code to generate the witness. Okay, so what I can do is, for example, okay. Well, first I will need. So this is circom. Circom is done. I just compiled. See what's. Let me show you here what's the flow that we are running, just to give you a map. So I start with a circuit. In circom, I generate like mainly I generate two things. So the WASM, or even could be a CTP. So it can be a program. Mainly, it's a program that computes the witness that executes this program. Okay, it executes this program, prepares that for making the proof. Okay, and then it generates our R1CS system. Okay, the program. So then I will need to generate an input and compute the witness. The witness is all the intermediary values plus the output of the circuit. Actually, it's the execution of the program, and it's used this WASM file. Okay, so I need to use this WASM file to compute all these intermediary circuits. Okay, and once this, then I generate a proof, and then the verifier just verify that proof together with the public. In this case, it would be just the output. Okay, so before using the prover and the verifier, in general, you need to run a setup. This can be a trusted setup. In the case of zk-SNARK, it can be a universal trusted setup in case of Plunk. So it's like you run it once and then it's a trusted setup. It's pores of tau. You can use an already generated trusted setup, and then for each circuit you don't need to run a ceremony. You just can use it. Okay. And from the setup, you generate two files: the proving key and the verification key. The proving key is the one used by the prover, and the verification key is the one by the verifier. Okay, so let's go and let's do it. Okay, so the first thing is I can generate, for example, well, first I need to install Snark.js. Snark.js is the tooling that we are using just for all the cryptographic, for doing the setup, for proving, for verifying. So first thing is npm install Snark.js. Okay. Let's see if it's finished. Okay, done. Okay, so let's. Well, the first thing is when you do a snark.js here, just you see all the possible commands that you can run. Okay, so the first thing is, for example, we go to start with something simple. Snark.js, for example, we can R1 CS files. I want to just info and get the, for example, is what's in there R1 CS. Okay, so well, here you see that's in the core VN 128. It has 4 wires, so it's a circuit with 4 wires. It has just one constraint, just a multiplication in just a single constraint. You can have there is 2 private inputs. There is one output. It's public output. All the outputs are public in general. Okay, so this is just some information. Okay, you can, for example, print the all these R1 CS. Here is just, well, this is a negative one. Mainly is A times B equals, well, the minus is, this is a constraint, okay? But mainly this is, here is some negative A times B equals, so the negative goes to the other side, there's negative 1. So just, but that's a constraint, okay? Just a single constraint, that's what it is, okay? So let's, in order to do that, okay, now I want to generate, first let's run the setup, okay? So let's run the, we need to run the setup. So to run the setup, okay, the first thing that we will need is, we are going to use now ZK snarks, okay? So to run the setup, you need to run a full ceremony, okay, if you want to do it in the right way. The ceremony has 2 parts, like a trusted universal ceremony, that's the powers of tau, okay, that has been already run, or it's still running in many places, and then the specific for the circuit, okay? In order, what I'm going to do now is I'm going to download the circuit, so the result of this trusted setup ceremony. In order to do that, I can go to snark.js. Here you can see a full tutorial of how to run. You can read it and go through this tutorial and how to run all these trusted ceremonies and so on. Okay, but the first thing that I will need is here is the powers of tau, is the result of the first part of the ceremony. So I'm going to get, for example, the first one, just copy link address, and then I get this address. So here, okay, so this is, I have this powers of tau 28 of for 200 up to 256 constraints. Yes, I have just only one, but this is going to be more than enough. If I have bigger circuits, I need to download a bigger trusted setup ceremony higher. Okay, so now I'm going to prepare the circuit. I'm going to run this preparation of the circuit. Okay, in order to do that, I just do snark.js just to see snark.js. Here is zk new circuit.r1cs. Okay, and I need to pass the powers of tau that I want to use. I get the R1CS constraint system. I get the powers of tau used, and I generate the circuit. ZK. Okay, so I generate the ZK circuit. Okay, so this is this one. Okay, so here I already have this circuit 000 ZK, which is the circuit. Okay, so it's with this we can. This is a proving key already. Okay, but this has no contributions yet. We need to run now the trusted setup phase, the second part of the trusted setup phase. What I'm going to do here is I'm going to run one step. Actually, this should be go from one from one participant on the trusted ceremony to the other, and jumping, and you do various. And as far as there is just one that's trusted, then it will work. So what I run here is a snark.js is zk contribute, okay, force of, oh no, this is not. Circuit 0, and I'm going to generate just the final, okay? Just the last one, okay? Just get one contribution and that's it, okay? So, well, this should work. Let's see. It asks me some entropy because here it generates a toxic value, and this toxic value should be delete. So I need to, that's the thing. Okay, so this is already run. I already have this circuit final.zk. So I already have a zk file. So I have the proving key. And now what I'm going to do is just generate the verification key. This is the proving key and the verification. Well, actually, it's the proving key and the verification key. So everything is inside. And what I'm going to do is export the verification key. So to do that, I just snark.js, zk, export verification key, and here is the circuit from the circuit final zk and the JSON. Okay. Sorry, zk. Okay, so I have the verification key, I have the proving key. So if you go here just to follow a little bit, here I already run the process setup. I have the proving key, I have the verification key, I generated the witness calculation. I need to, and now let's run a one proof. Okay, so I need an input. Okay, so I need an input. I need to generate. Okay, so for example, let's choose two numbers. For those, this is just input.json. Okay, let's create a simple JSON. JSON an A. Let's put, for example, a number 34, and then the second number, just put, for example, B. Let's put 10. Okay. Okay, I have these two numbers. Okay, and now I need to run the circuit. Okay, I need to generate a proof. Okay, so I'm the prover. So actually, I want to prove that so given 34 times 10, this is 340. So I want to generate a proof that I know two numbers that when you multiply it together, the result is 340. Okay, so well, let's run it. Okay, so in order to, I'm going to execute now this section. Actually, I'm going to generate all these intermediary signals. To do that, it's snark.js. This is witness calculate. I use the circuit wasm, and the result, well, is input, the input.json, and the result is going to be witness. Okay. Okay, I already generate the output. In order to see the witness, what I can do is export. This witness is binary. Okay, so I can export to a JSON to see it. So what I do is witness export JSON witness.json witness.json. Okay, so if I just get witness.json. Okay, here is just all the signals. You see, it's the 340 is the output, and then I have the two inputs, the two signals. I have one intermediary value is 1. That's the first one. It always exists. But if you see other circuits, you will have all the intermediary values. At the end of the circuit, you can do additions and multiplications in general. So all the partial results are here. Okay, this is what need the witness. Okay, so I already execute that. I prepared that, so I have this witness file that's prepared, and now let's generate the proof. Okay, so in order to generate the proof, is snark.js. I'm going to use growth16 proof, and then here is I need to pass. I think need to pass is the circuit. So the proving key. I need to pass the witness. Just, well, I don't remember. Just let me. Growth16 proof here is in here. So it's snark.js, growth16 proof then is circuit final JS witness. I want to generate the proof, the JSON, and the public.json. Okay. Okay, the proof is generated. You can see the proof. Okay, this proof is actually, you can see it's A, B, and C actually are 3 points. Okay, this is the growth 16 proof. You can see it here. Okay, and the other circuit that generated is the public.json. This is just a subset. Actually, it's just the output. It's just the public signals. Okay. In the witness, you have all the inputs and all the intermediary values, and in the public part, you just see the public signals. And actually, this is what you need. This is the result. This is what you need to prove. So here is I'm proving that. So this proof proves that the person that generates the proof knew two numbers that when they multiply them together, the result is 340. In this case, it's 54 and 10. Okay, but the thing is that you can give this information, you can pass this proof to a third party, and this third party, you don't need to reveal which are those two numbers, and this person will be convinced that these two numbers are okay, these two numbers. When you multiply together to go 340. But if you don't know these two numbers, it's impossible to generate the proof. Okay, so this is the concept of the zero knowledge. Okay, we have the proof. Now I want to verify the proof. In order to verify that this proof is valid, then just Snark.js, here is growth 16. Well, just let me just Snark.js is growth 16, verify. And then I just put the verification key, the public part, and the proof. You verify, and okay, that's good. Okay, so that means that the verification is correct. Okay, but this verifier, the cool thing of this verifier is that, okay, I can verify it here. It's with Snark.js. Snark.js is a library that you can import in your project, and you can do all these operations in kind of SDK. So you can put inside you, and you can do everything inside your JavaScript code. Okay, but what happens if I want to verify that in a smart contract? Okay, so I want to have a smart contract that you pass a parameter. So you pass this a proof, you pass a public part, you pass a proof, and the smart contract returns true or false if this proof is valid or not. Okay, this is one of the coolest things of Ethereum. You can do that inside the smart contract, and this is the base for many applications. Rollups, for example, we'll see it later. Okay, so let's generate the Solidity code that generates this proof. Okay, so in the Snark.js, CK sport Solidity verifier. So, and then it's from the circuit final, and then so I generate a verifier result, just a Solidity code that actually verifies that. Okay, and Snark.js does that everything for you. Okay, so I run it, and here I have the Solidity, the full Solidity code that generates so that verifies this. Okay, what I'm gonna do is just I'm gonna deploy this smart contract. Let's start here. Okay, just cut, and then I'm going to remix. Okay, I'm going to generate here I have a verifier. Okay, let me just well, just delete everything. Just copy the verifier. Okay, I go sorry, just here I compile with optimization. Solidity 061. This is done automatically. So I just compile. Everything is okay, and now I'm going to deploy it. Okay, I'm using I'm using Web3 here. Okay, well, let me just connect maybe to my MetaMask. Yeah, it takes a while. Okay, I'm in Rinkeby. Here I'm selecting here the verifier. That's the smart contract that I want to deploy, and let's go. Let's verify that in Rinkeby. Let's deploy that in Rinkeby. Okay, so creating the verifier. That's me to sign. Confirm. And well, now let's wait for the verification. Here it is. It's already. I have, well, this is, sorry, let me just bring contracts. Let me just deploy it again. Okay, here is. Here you see is this verify proof. Here I should pass the proof. If you see here, you have to pass the proof, and the verify proof you have to pass the proof, which is these 3 points plus an input. That's just an array of 1 because the input is the public input. In this case, it's just an output. It's just one single element. It's a public output. Okay. So here I should pass the proof and the proof. In order to do that, Snark.js has a tool. It has an option. That's Snark.js ZK export, and then is Solidity. Political data, and then I purchase the public.json, the proof.json, and it just generates here. Here, what I'm just doing here is I'm just putting the public.json and the proof.json, so the proof and the public just in a way that I can just cut and paste. But this is just formatting this in a format that the Remix understand, or that the normal Web3 call understand. Okay, so I just copy here, I just paste it here. Okay, so here is the last number is this 154. This is the this is the output. This is the 340 in hexadecimal. Okay, this is 154. Just verify. Let's run it, and the result is true. Okay, this proof is valid. Okay, just for you, if for example, if I change something, for example, I change the last one, which is the input. Okay, so just say, for example, here 153, for example, and then I just verify, then it's false. Okay, but this is done in a smart contract. Actually, I'm calling a smart contract right now. Okay, so the cool thing is that you can generate your circuits and zero knowledge verify it in the Ethereum network. Okay, so okay, this is the first part of my presentation. I'm a little short in time, but let's move forward. Okay, so okay, how we apply that? How do we apply that in to scale Ethereum, to create a rollup? Well, as you can see, and here is the important part here. Let me just run here to here. The important part of Snarks is not the zero knowledge for scaling. The important part is the S. The S is for succeed. The succeed is this property that you can generate a proof that's you can verify that proof very, very, very fast, much faster than what it takes to compute to calculate to execute the circuit itself, to execute the program itself. Okay, and this, I think, this difference between the verification time and the proving and the execution and proving time, that's the succinctness, that's the S of succinct, and this is the important part, and this is what makes everything scalable, and this is where this is the breaking the breaking technology that actually allows scaling blockchains in general. Why? Because until now, if you think how it works, all the Bitcoins or Ethereum, any blockchain, how it works is somebody just proposed some transactions, and those transactions needs to be verified for all the people in the network. Okay, so all of them, they need to verify that they need to run a program. It's a deterministic program because the rules of if a transaction is valid or not, they are very well defined and very clear, but they need to verify that these transactions are okay, and this needs to be run for all the transactions, for all the members of the blockchain to reach this consensus. Okay, and the limitation is mainly that you need to go like to the slowest one. So the slowest one in the network is the one that has this bottleneck in some way, and this is why blockchains until now it doesn't scale. But with this technology, I can put in a block, or I can put so I can just a miner or whoever just can put the transactions that's processed, can put thousands or even millions of transactions, just this data, and the people don't need to run to verify all the transactions. There is no need to verify transactions. They just need to verify a proof that all these transactions are valid. Maybe they need to hash them together, all the data, and then you have a state. You know that this data and this state, you just get you pass a circuit, you go a deterministic program, it gives you a state, and then you just verify that everything is okay, that all these transactions are well signed, that all these transactions the transactions have enough funds, that all the verifications that needs to be done in the rollup. So and the cool thing is that the verifier, so maybe there is one that needs to create a proof, which is expensive, okay? But the consensus layer, they don't need to verify all the transactions. They just need to verify a single proof. And the cool thing is that this proof, it's just a few milliseconds. And I would say that theoretically, it doesn't matter how big is that. It could theoretically, it can verify like millions of transactions. Actually, there is some technical limitations right now in the kind of curve and so, but theoretically, this can grow a lot. In Hermez, for example, we are in a single proof, we are verifying 2,000 transactions in a single proof, and this is a single proof that it takes few milliseconds. Or if you want in gas terms, it takes less than 200, 300 K gas. So it's just quite very cheap. Okay, compared to that. Okay, and this is the important part. So how a rollup works? Well, rollup is very much about that. So you have a rollup is something that's running on top of or just let me here, just clicking. It's running on top of Ethereum. So the idea is that there is a smart contract that's keeping a state. You have imagine a state is all the accounts and each balance. You have all the full state of the accounts and balance, and this is the state is Merkelites and keep it in a smart contract. And then this smart contract accepts new transactions, and each transaction we call it a batch. So it's like I give you a set of transactions and I process these transactions, but the transactions are just compressed in an array of data that's in the call data, and the smart contract just verifies that these transactions actually fulfills all the rules, and then you have like the newer state with all these transactions processing. Okay, just let me here. Okay, so you have different batches. Each batch is a transaction in a smart contract. In each, so you have a state with all the public, so with all the states, so for which is with each public key, how much has of each coin. You have this state. You have a set of transactions. You process in each batch. You process these transactions, and you evolve these transactions in a rollup. Okay, so that's you are evolving, and the interesting thing is that okay, you can these transactions if it's full packet and all together, it takes more or less a little bit less than 1 million gas. Okay, so theoretically, if we use the full Ethereum just to process these kind of transactions, this is right now with 2,000 transactions per second, we can process 15 batches each block. So actually, this gives that a total number of 2,000 transactions per second, more or less. Okay, this will be, of course, using the full Ethereum, but this is like 2 orders of magnitude more that how much transactions support Ethereum. And this is just like the first version of this of the rollup. It's like the first rollup, the first rollups that appears. But you see how all these things scales. Okay. We have been talking a lot about the validation proofs. Okay, but actually there is another part that's important. So it's not enough to send the proof to the smart contract. You also need to guarantee that all these transactions in a compressed way, you don't need to process them. You don't need to verify that they are okay, because this is done in the proof. But all the information that's in these transactions needs to be available. People needs to know what are the transactions. Okay, so this is what we call the data availability. Data availability, you don't need to. So data availability is not as hard as consensus, because as far as there is just one person that keeps this data and makes them available, the data will be available. It's not that consensus that you need like 2/3 of the people in the consensus systems to have a consensus. But it's important, because if not, a validator would, a coordinator would just generate some new state that's valid, but then nobody knows how to build this state, so the network will be blocked. So, and in the case of zk rollup, in the case of Hermez, what we are putting is we are compressing all this information and putting that in the call data. It's not in the state; it's just in the call data. This is very cheap to put it, but it does not take space in the Ethereum, but it's available. Okay, this is part of the transaction call data, and we put that there, so everybody can reconstruct all this state whenever they, if it's required. Okay, so it's available. This is that availability. There are other techniques here. I'm very optimistic with Ethereum 2.0, especially the sharding part. So all this Ethereum 2.0 mainly is going to be like data availability system. So people will be able to put this data in in many shards, and then you will be able to prove that this data is available. So here is when you combine Ethereum 2.0 with data availability with the rollups. This is when you get the full scalability picture on that. Okay, so yeah, so here is well, a rollup circuit. So how a rollup circuit is, at the end, it's a deterministic program. Well, you can imagine how it works. Mainly, it's you have a sub-circuit that's to process transactions. Okay, I get from a root, also a state. I process a transaction, so get a new root, process transactions, and you do that 2,000 times. Okay, and this is what mainly is the idea of a circuit is about that. Okay, and all these circuits, for example, in Hermez, this is written in Circle, is written in the language that you see before, but you have like many circuits there, and all the validations and all the stuff, and everything is compressed there. Okay, so yeah, if we zoom in to a circuit, of course, you need in this circuit, you need to verify the signature. We need to verify that we need to Merkelize that. We need to verify that the current state is the right way, that the new state is the current state of the two accounts that affect are okay. You change it, you compute the new states. This is all the root part, and then all the transaction processor. You need to know that you have enough funds. So all this validation, this is done already inside the circuit. So that means that you don't need to run the program. You don't need to verify that the transactions are okay. This is guaranteed by the proof, by the full proof of the system. Actually, for example, we don't even keep the the signatures on chain. Signatures are not available, okay? But we verify them. They are like private inputs. So you know for sure that this transaction is valid. So you know that that this transaction was signed in the right way, but you don't need to keep the signature. You just know that it was okay, that the signature exists, it was valid, and you have this warranty. So for example, that the signature is not required to be in the data availability field. So this is why you compress a lot. You have actually, if you see a transaction, it's only the from, the to, and the amount and the fee, and that's mainly what it is. And this is very compressed. Okay. Okay, let's move forward. Okay. Yeah, a couple of words about token economics. Here is Hermez is a decentralized system. Right now, it's a little bit centralized still, but the protocol is decentralized, and the idea is. And here, the big point of centralizations of these rollups is, okay, who's building this proof? Who's the one that, who's the coordinator? Okay, so this is the thing. And in Hermez, so there is in many rollups, this is just a central people. It's just a centralized system. Okay, in Hermez, this is not the case. This is decentralized. So anybody can be a coordinator. Okay, and in order to select a coordinator, what we are doing is we are using what we call a proof of donation. Mainly, it's an auction. So what you are doing is you are buying 10 minutes slots, and the idea is that in that 10 minutes that you buy, you can forge as many badges as you want or as you can. Okay, so and this is an auction system. The people is bidding, the people and the winner of this auction is the one that's the slot is assigned. Okay, so this is very much, and these tokens that are collected from the bidding, these are, well, part of it is burned, part of it is donated, and part of it is reinvested to the people that's using the rollup. Here there are some attacks, and here is what we are well, it's very much is that there are some attacks that maybe somebody could attack the network by just buying the circuits, by buying these slots and don't forging slots. And here we have different types of slots. Okay, some of them can be like fully decentralized, and some of them we can at the beginning we guarantee at least until the network is fully working, that we guarantee that in these specific slots are forged by the boot coordinator. But this at the moment that there is more transactions, this should be just every time more released on that. Okay. Yeah. Another thing is on-chain transactions. Another possible attack of rollups is that people can it's the censorship resistance, because if there is very few coordinators, what happens if a coordinators don't want to forge your transaction? Okay, so for this case, we have what we call it L1 transactions. L1 transactions are, for example, a deposit. So when you want to move funds from the layer 1 to the layer 2, withdraws. Okay, when you want to remove, but you also can do force exit even. And the thing is that these L1 transactions, operators are must if they want to, so they must forge. They are obligated. They must forge those transactions if they want to forge specific a batch. So it's either they forge those transactions or they don't forge anything. But if they don't forge anything, there is a timeout that then anybody can forge a batch. So in the worst case, you can always remove your funds. Maybe you will not be able to use it to do transfers, but you will always be able to remove, so that your funds will never be locked in the rollup. Okay, this is what forced transfers or forced exits, layer 1 case. Okay. Yeah, a couple of words about atomic swaps. Hermez, for example, supports atomic swaps. That means it's a transaction that's conditional to another. So you can say you can send these funds to this person, but only if this person send me these funds to the other. Typical is, for example, for a token swap. So I want to swap, for example, Ether for DAI, and so I make you a transfer of Ether to another account, but it's a conditional transfer. That's only if there is another transaction that sends DAI to Ether to this account. Okay, so this is what we call it atomic transactions, for very used for mainly used for atomic swaps, but have many other applications too. Okay, and you can link different transactions to 1, 2, 3, 4, 5 transactions. You can link it in an atomic way. Okay, the roadmap, we have one. We're working in a kind of a token, an atomic swap on top of Hermez. It will be available. Hope that very soon, but we are developing it, and it's used this property of atomic swaps that's already implemented in the protocol. Okay. Yeah. Just to finish, just mention here, I'm not going to go deep, but Hermez also supports a full massive migration system. The idea is that you can move. So the idea is when you want to move funds from one rollup to another rollup, you can always do it via layer 1, so you can do a withdrawal and then a deposit in the other side, but this is quite expensive. So the idea is that you can do it that in an aggregated way. So if there is many people that wants to go to another rollup, they can, all these transactions can be aggregated in a single layer 1 transaction. So in a layer 1, you transfer the sum of all the funds from one to the other, but and then so you just pack all these transactions to a single L1 transaction, and then one transaction is just then redistributed back to the different accounts. Okay, so there is a full technique that's prepared. It's very early stage, but we are also working in this. We call it massive migrations. This is a mechanism that we will start here a lot in the upcoming months or years for interconnecting these layer 2 solutions. So that's a little bit the end of my presentation. Anybody that's interested to hear, just connect to the Hermez Discord. Also for the Circom stuff, there is the IDEN3. Here is the IDEN3 Telegram group, and there is a very good community just specific to Circom. For more generic to Hermez, just Hermez Discord or Hermez Telegram group, but Hermez Discord is probably the best way to reach us, and we are absolutely open to any questions, suggestions, collaborations. We are hiring developers. It's like we are absolutely open. So just please contact us if for any question you have. So. Yeah, that's the end of my presentation. Let's scale, and that's all from my side.
Jordi, thank you very much for your presentation. I can see we just have a question from the audience. It's not really about Hermez Network, but about TrueBit. Do you have any opinion on their solution?
TrueBit is for proving. I think I hear.
I think it's a project that enables more advanced computing on chain.
Yes, for proving computation, but there is a kind of a game. I think there was a kind of gaming system that's like it's a challenge, and then you can prove a full computation smart contract by just doing this game. The cool thing of this goes rated, for example, for optimistic rollups. Optimistic rollups at the end is they don't do this zero knowledge. They just put the value, and then there is this gaming mechanism. This is the gaming mechanism. You can challenge that's not wrong, and then you can move forward. The cool thing of ZK Snark is that you don't need this challenge game. You just put the proof. The proof is valid. Block is processed, done. You don't need to worry about. And this is very cool. Of course, you need to build this proof, which is more difficult, but the technology is growing very fast and a lot. And I personally think this is the real future of blockchains. You go to optimistic rollups, all this gaming mechanism. I'm a little bit skeptical. You start getting you start seeing a lot of edge cases, complexities, and the end users needs to be aware of what's going on. This is much more simple. So a ZK rollup is much more simple in concept than an optimistic rollup. Okay, so you need to build the proof, but this is the complexity. But if building proof is cheaper, faster, and good, and this is growing and it's just growing, then I would say that optimistic rollups have no sense if you have the other thing. While this technology, this zero knowledge technology evolves, well, the while optimistic may have a lot of sense.
Okay, thanks for the explanation. Jordi, I won't keep you any longer. I know that you are in a hurry today. So thank you very much. I appreciate your time today.
Thank you very much to you.
Yeah, safe travels.
Perfect. See you guys.
Thank you, Jordi. Bye-bye.